So let's go on now to talk about Newton's laws. Newton's laws of motion. Now there are three of these, and so we'll say what these three are. And it will turn out that the second one is the one that you use the most often, and it's the one that has a specific equation associated with it, namely this F equals ma. But we'll list them all. So the first one says, it's usually stated something like this. It says a body at rest remains at rest, and a body in motion remains in motion along a straight line at a constant speed unless acted upon by a net external force. So this is a very detailed and careful way of saying exactly what the first law of motion means. There's ways that you can simplify this. So let's think about what this is saying. And say we take, some simple situation where I have say I have a mass that's sitting on a plane. A good example is like, an air hockey table, where there's not much friction. So you have this puck that's suspended by the air on the surface of the table. Well, if it's not moving, it will just go on sitting there if you don't apply any force to it. Whereas if it is moving, it will keep on moving unless a force is applied to it. You see this all the time when you're driving. I mean, if you see an accident in front of you and you try to stop, you see that the natural thing for your car to do is not to just stop on its own necessarily. The natural thing for it to do is to keep on doing whatever it has been doing. If it's stopped, well then it's not going to spontaneously start moving without a force applied to it. But if it is moving, then it's not going to stop without a force being applied to it. So this is what the first law says. And you can boil down all this at rest remains at rest and in motion remains in motion along a straight line at a constant speed by just saying that the velocity of an object doesn't change unless there's a force that's applied to it. And that leads us directly to Newton's second law. And what Newton's second law does is it describes how the motion of an object changes if you do apply an external force. And so this is usually, you can be as sophisticated about it as you want, but it's usually expressed by this equation, F equals ma. And so what this says is net force, let me go ahead and capitalize this because I capitalized that one there. So the net force on an object is equal to its mass times its acceleration. Now, this describes a relationship. You have an F on this side, you have an MA on this side, And so the equal sign kind of goes both ways. I mean, that's how an equal sign goes. This is equal to this, and this is equal to this. But of course, you actually think about this in a directed way, in the sense of cause and effect. You say the force causes the acceleration. So you don't just say you don't just think so much that the force happens to be equal to the acceleration, as you think, well, you apply a force and that makes the object accelerate. The force causes the acceleration. So there's a cause and effect relationship happening here. Now, there's other ways to describe this. I mean, if you had calculus, you could say force is the time derivative of the momentum. So this would be P is the momentum, and this dP dt. And the momentum in some contexts is m times v, mass times the velocity. And so now there's details, but this sometimes you could say, well, this works out to m dv dt. And you could say that works out to m d squared x dt squared, where x is the position. But we don't really need all these details. And then, of course, all this is sort of superseded by the general theory of relativity. It gives you corrections to what this F equals ma does, and we don't need to talk about that either. This will do for all our mechanical problems. Okay, now I want to emphasize here that it's the net force that appears over here in the F. You know, for instance, you could have a block that's just sitting on a flat plane like this. And so there's two forces. There's mg, the force of gravity pulling it downward, and then there's the force mg from the plane pushing upward. They exactly cancel each other. There's no net force on the block, so it doesn't move. Now, that doesn't mean there aren't forces on it. There's a force down, there's a force up, but there's no net force. So you have to always be careful when you're putting in forces that you don't miss any, that you put the net force, the sum of all the forces, into this F equals ma. All right. And then the third law is, this is the action-reaction law, and this is often stated as, for any action, there is an equal and opposite reaction. And the prototypical picture of this is the thing I just drew, where you have a force of gravity pulling an object downward this way, and then you have the plane going up. When I'm standing here on the surface of the Earth, I have a force of gravity pulling me downward, right? Why don't I fall down to the center of the Earth? Well, it's because the floor is pushing me upward. So I have a balance of forces. And so no motion will give you a balance of forces. Now, this action-reaction thing applies even when there's not a balance of forces. You know, for instance, if I apply a force, like say I'm pushing, say this is a big box and I have this person here who's pushing on the box. So on the box here, there's a force going that way. It's being applied by the person. Now, the net force on the box is not zero, and so the box will slide. But the box does push back on the person with an equal and opposite force. So the fact that there's an action-reaction thing, and you could say, okay, well then why doesn't the person go this way if the box is pushing on the person this way? Well, the person's feet are contacting the ground here, and the ground is pushing this way on the person. And so in this picture, those two forces cancel, and the only thing that moves is the box. But this action-reaction thing says for any action. It doesn't say for a balanced, set of forces. For any action, there's an equal and opposite reaction. But that doesn't mean nothing moves. In this case, it's true that nothing moves because the forces on M are balanced. In this case, it's not true that nothing moves. M does move because the forces on M aren't balanced. There's still a reaction force on the person, but the force on M, the force on the mass here, isn't balanced. So that's a little bit of a subtlety in terms of how this action-reaction thing works. Okay, so we already talked about inclined planes, and I'm just going to very briefly revisit inclined planes here. I doubt if there's going to be detailed quantitative questions about inclined planes on your test, but this is inclined planes revisited. And so the way the picture looks, and here I'm going to draw the whole thing, not just the free body diagram. So we've already drawn this several times. So there's going to be an angle. This is the angle of the plane. And it will turn out that there's, well, I'm not going to draw the net, I'm not going to draw the total gravitational force. I'm going to break the gravitational force into two components. And this is going to be the component that goes this way. And this component happens to be mg cosine theta, where that's theta. And then there's the component that goes this way, and this is mg sine theta. So both of these would be components of the gravitational force, which would be mg. And if I'm going to draw it and then erase it. This would be mg going downward like this. But I don't want to draw that there because it's not independent force. It's the force you get by adding together these two. So let's just draw the components. So I have an mg cosine theta going this way and mg sine theta going this way. I don't know why I drew these as dashed arrows. There's no need to do that. I'll just draw them as solid arrows here. Now, the plane pushes back up on the block, and this is the same magnitude of force. This is mg cosine theta. Now, of course, if I'm thinking of these as vectors, the signs are really different, and so I could either put a minus sign there, I could put a minus sign there. But since I've drawn the arrows to indicate the direction, and since we won't actually really need to use the signs, I'm not going to specify a sign here or a sign here. This thing has a name. It's called the normal force. The word normal is a synonym for perpendicular. So it means the force exerted perpendicular to the surface of the plane. Orthogonal is another word. Perpendicular, orthogonal, or normal all mean the same thing in this context. That's the normal force. And then finally we have the force of friction. Now, as I've written here, the motion of the block on the plane is always going to be determined by this part, the mg sine theta, and this part, the friction part. And that's because the normal force and the component of force into the plane from gravity cancel each other. So the motion is always determined by, so motion is determined by two things. It's determined by this mg sine theta and the force due to friction. Now, so then why do we care about the normal force at all if it doesn't determine how the block moves? Well, because the normal force goes a long way to determining what this force of friction is. And one way of approximating what this looks like is you have this is the same letter mu, but it means a slightly different thing in this context. It's not just a label, it's actually a value here. And then this will be mu mg cosine theta. And this thing is called a coefficient of friction. And this would be equal to this. The point is that this is how you determine what the friction force is. So the reason you care about the normal force is because oftentimes you can write the friction force in terms of the normal force like this. I don't see any reason to go into any more details about this or numerical details. So the punchline for inclined planes is that this is what's going to determine the motion. In particular, if there is no friction, then the block just slides down the plane and its acceleration is just given by g times sine theta, because the mass isn't going to affect the acceleration. So inclined planes is always the mg sine theta, the component of the gravity down the plane and the friction force. And I say here versus because they point in opposite directions. Friction always resists the actual direction of the motion. Let me say a few more words about friction because it's a common phenomena. So friction. This is one of these electromagnetic forces, which is complicated, but it arises from electromagnetism. And there's different ways that this shows up. And this is, so the one we just seen, so this is force on block on plane. This is a specific type of friction that comes from contact between two rigid objects. And then another way is what's called drag, and this is the same thing as wind resistance. Well, wind resistance is an example of it. And this is also friction, and what's happening with wind resistance is that you are going through you're moving through some medium which isn't rigid, and the medium that you're moving through is resisting your motion. So it's once again, it's resisting motion, it's pushing back, and it has to do with contact, but it's not contact with another rigid object like it was with the block and the plane. It's contact with the air or water or something like that. And then you can have something like viscosity. So this would, you know, like, well, this is, so e.g., like if you have honey, flowing. I don't know if you've ever like had one of those big jars of honey on a cold day and you tip it over and you're trying to, maybe it's like a plastic bottle and you're trying to squeeze the stuff out, or maybe you're trying to spoon it out and it's really thick, or maybe you're like stirring candy or something like that. So that's all, what this is called resistance to laminar flow. So this word laminar, you know, if you laminate something, you're like putting together layers of plastic or something. So this is the idea of layers. And so here you have a substance which is like a fluid. And so you can think of layers of the fluid sliding past each other. And this has many applications in medical contexts. I mean, anything involving fluid flow, whether it's the circulatory system, or if you like have somebody hooked up to an IV, or any number of things. So this is also a friction thing, and this is how much do different layers of the fluid resist moving past each other. If you have something like oil, it has a low viscosity. It slides very easily. That's why it's a good lubricant. So this comes in, you know, in medical settings, like if you're giving an ultrasound, you have to put some kind of lubricant, like you're doing an ultrasound of somebody's heart. You put this lubricant on it so you can slide that, you know, little ultrasound around on it. Versus if you're putting these EKG things on somebody, that sort of fluid, the glue that you're attaching to, it takes like 4 or 5 days for you to get it all off. So that's a contrast between something that has a very low viscosity, very low contact friction, versus something that has a very high contact friction. That's all friction. And so this friction thing, it all shows up in different contexts. And it's always close scale contact type resistance of one object or body to another. You have just here the 3 examples where you have 2 rigid bodies that are close to each other, and then one where you have a rigid body moving through some sort of substance, and then one where you're thinking about a substance moving around, how it relates to itself. These are all different ways that friction can manifest itself. All right, so we have one more topic to discuss, and this is, so I guess I should have been checking all these off. We've talked about all these things. This is Hooke's law, and this involves spring forces, and it also involves a lot of other kinds of forces. And so one thing it involves, and I can use a big rubber band to represent this. So this is kind of like a spring. Now what Hooke's law says is that if I deform this, in this case if I stretch it, then the amount of force that it exerts is going to be proportional to the amount that I stretch it, and it will point in the opposite direction. So if I stretch it this much, then it's going to pull back toward me at a certain amount. And if I increase that to twice what it was, it's going to be pulling back toward me at twice that amount of force. And so this is usually expressed in terms of springs, because with a spring, you see with the rubber band, I can stretch it and it will behave this way, but I can't really compress it. It doesn't have that compressive thing. If you take a spring where you have, like from a notebook, then it will have the same sort of behavior whether you press it or whether you stretch it. The way you move it, it will always resist whatever that motion is. It's called a restoring force because it tries to restore it back to its original shape. And so I've drawn a picture here where the spring's not stretched, and then where it's stretched by a certain amount, which I call delta x. So just in a little bit more detail, this Hooke's law. What I can do is I can imagine a spring that's attached at one end to a wall, say. So this is stuck here. And then the other end, and sometimes people will like put a mass at the end and then think about the motion of it. But we're not going to do that right now. We don't really care about the mass. So this is going to start out, it's going to stretch out to a certain point, and I'm going to call that point 0. And what I'm going to do is then I'm going to proceed to draw a coordinate system where the x direction goes this way. So if I take this thing and then I stretch it, so what I'm doing is I have this point. Now there's nothing physically here. This is just the point it stretches to, and that's why when it's not either compressed or stretched out, it just reaches up to that point. Well, I can take it and then I can stretch it out like this. And this amount that I stretch I will call delta x. The delta means change in. So this is change in x. And there's a force. So I'm pulling on this. You know, I grab the end of the spring and I pull it beyond this point. It's pulling, and the further I pull it, the harder it's pulling back. And the amount that it's pulling, so it's going in this direction, and so it's going in the negative direction from the way I'm pulling it. And the size of that force is going to be some number k, which depends on the spring. It would be a different k for a different spring. And then there's going to be a minus sign, and the minus sign tells me that the spring is pulling back against what I'm trying to do. And then there's going to be delta x here. So what does this say? This is the amount that the spring is displaced. That's the delta x. And then the k is what's called the spring constant. And then the minus sign says this says that it's a restoring force. And so restoring means that the spring wants to restore itself to its original configuration. It wants to move back to where it wasn't stretched. And the same thing would be true, you know, if I draw the picture and I have this distance here, and say I compress the spring, you know, say I press the spring this way, well then the spring itself is going to be pushing back against the way that I've pressed it. So once again, in this case here, the delta x is negative. So now the force of the spring will be positive. It will still be negative k delta x. But since the delta x itself is negative, that negative will cancel this negative and will give me a positive force, which is why I've drawn this force here as positive. So that finishes up all the theory in the first chapter, and we still have a few problems to work.